Good morning, dear colleagues. Thank you very much for allowing me to present some results in the field of nonlinear optics. I a little bit changed the title from advancement of nonlinear optics to achievements in nonlinear optics, since I think that it is more suitable for this presentation and for the links between my scientific interests and the interests of the Institute of Atomic Physics and Spectroscopy. So, I'm Rashid Ganeev from the Laboratory of Nonlinear Optics, Institute of Astronomy, University of Latvia. Nonlinear optics is a quite broad field, and as I added here, this field of optics explains nonlinear responsive properties, which span in quite broad range of the characteristics of media, and it covers a huge range of the effects which I just marked there by blue color. I do not want to talk about all of them because it do not take enough time for me during this day. So I concentrate on few parts of them which I marked by bold, and I will tell about some achievements which were shown during my studies of those effects. Here I presented some intensity range of activity. Below you see this x-axis where I put laser intensities on the surfaces, and inside the media, which spans from 10 to 0 up to 10 to 23 watt per square centimeters. During long time of my activity, I worked with laser rangefinders, laser matching of matter, laser therapy, art cleaning, non-ripples formation, clusters formation, and X-ray lasers. But those are out of the scope of this seminar, where I intend to put some fields which are spent in the range of nonlinear optics. Those are surface-enhanced nonlinear optical processes, low-order nonlinearities, surface nonlinearities, plasma harmonic generation, and surface harmonics. I carried out those studies around the globe, and I briefly tell about some of most interesting achievements in those fields. Initially, I worked with low-order harmonics generation of laser radiation in various media. Those are first stages of nonlinear optics, which were allowed to analyze in all times due to the absence of the strong laser fields, and I studied those processes in many materials. Other fields are related with the compression, nonlinear compression of laser pulses in nonlinear crystals, and I demonstrated laser pulse compression during second harmonic generation in KDP. And third field is analysis of the third order nonlinearities of some metallic ion beams like gallium ion beam. And in those times, some practical applications of nonlinear effect like second harmonic generations were used by me in creation of the strong green light, communication with satellites, and with submarines. Probably you know that the seawater is not allowed propagation of the electromagnetic waves in most of the spectral range, but green color is more or less good propagated for communication with submarines. So our main aim was to increase conversion efficiency and make communication with those submarines. Another interesting application of nonlinear optics is related with creation of some films which allowed optical limiting. Why it necessary and what means optical limiting? It means that at some range of intensities, propagation becoming the same, but with the growth of intensity, it dropping, and in some cases it dropping significantly. So by other words, it can preserve sensitive equipment and eye against destroying. And the practical applications is protection of satellites against overexposure by laser radiation, which in some cases can significantly destroy the registrars of satellites. Another field of nonlinear optical studies is another. Instead of optical limiting, when with increase of intensity the transmittance of material dropping, we can create conditions when with increase of intensity, for example, close to the zero position in Z-scan, transmittance increases. It is so-called saturable effect, saturable absorption effect, which has been observed earlier as a bleaching in many materials, but in some cases we can create conditions when it could be very useful for creation of conditions of Kerr effect induced processes like Q switching, module locking, and other methods of shortening of laser pulses inside a laser system. And third method is the third harmonic generation in air. It is a well-known process for in the case of femtosecond pulses. However, in some cases we can create conditions when relatively smooth Gaussian shape can be changed in different shapes, and we can create some sort of filaments of third harmonic generation, which could be useful for propagation in air for long distances, since, as you know, filaments are propagating for a long time once you create specific conditions of focusing. Another important analysis of third harmonic generation is the use of this process in laser-produced plasma, in laser-induced plasma. Picosecond pulses or nanosecond pulses create plasma in vacuum chamber on some specific target. And then with some delay, femtosecond pulses propagate through this and analyze it by simple any of the spectrometers, which can be sensitive in the range of 300 nanometers. And what we can see, we can find conditions when the optimal condition, when maximum conversion efficiency going with the growth of intensity, and after that it dropping due to some saturation and other processes. And we can find conditions how to ablate those materials to analyze nonlinear opticals of the samples. It's some sort of the first step of laser-induced low and nonlinear optical spectroscopy. With this method, it is possible to analyze some carbon-containing materials. Particularly once you ablate carbon-containing materials, you can see very strange shape of the distribution in mass spectra when only spectra between carbon 5 to carbon 30 can be seen from here in this mass spectrum of the ablated materials of carbon clusters after ablation of carbon. And you can use further them for the efficient harmonic generation, initially for low order harmonic generation and then for high order harmonic generation. Apart from solid materials, interesting gas is xenon. it allows to analyze the conversion efficiency in the range of the anomalous dispersion of xenon in the range between 113 and 117 and so on. And I analyzed those processes and just shown how the oscillator strength of this material nearby to some strong transition change the conversion efficiency towards the third harmonic, which allows optimize the process, this process, and create tunable sources of vacuum ultraviolet radiation using third harmonic generation. Next step of those studies was the analysis of the high order harmonic generation. How it can be happened. I analyzed boron plasma and demonstrated that in some cases, at specific conditions of boron, excitation of boron, very strong emission in the range of 6 nanometers appears, while no other lines, almost all of them almost not exist, and only 6 nanometer radiation. This radiation could be used as the probe material both for analysis of organics or even for the modification of those organics in XUV range. And once I analyzed this, I just found that the specific conditions of ablation of boron target, instead of this spectrum, here I shown the spectrum at 6 nanometer and the higher order, second, third order diffractions, I obtained this strange spectrum. And I immediately understood that I found conditions for high order harmonic generations. This is first EVA spectrum when high order harmonic generations were obtained up to 63rd order of the titanium sapphire laser. I can say briefly that historically only harmonics up to 20th harmonics were observed, and I have demonstrated with the optimal ablation of materials we can generate harmonics easily between 60s and up to 100th order, and with the specific feature like plateau-like range distribution of harmonics, while all other cases demonstrated in many papers did not demonstrate those features. And this was the beginning of the era of high order harmonic generation, and some specific features I will show later on. I demonstrated some interesting features while analyzing the different shapes of laser plasma. Nonlinear optical properties of laser plasma when it appears as an extended plasma, just shown that spectrum is, could you see this red color, is a homogeneous plateau-like shape is very small conversion efficiency along all the spectral range. Here I just shown harmonic between 90th and 51st orders and in the range of between 15 up to the 45 nanometers. However, once I divided this plasma using multi-slit mask by 3 plasma jets or even by 8 plasma jets, I obtained was able obtaining 1 or 4 or 8 jets. And once this femtosecond beam propagates through these jets, occasionally appears a group of harmonics which significantly stronger than the harmonics which were observed with in the case of imperforated extended plasma. It is so-called quasi-phase magic effect, when for high order harmonics you can create optimal conditions for high order harmonic generation. Once you change distance between the slits and the distance of a number of jets, you can smoothly change spectrum from one range to another range. Just show how it looks like. This is very slim spectrum of harmonics from the extended plasma, but once we put multi-slit mask, we see this spectrum, this and this spectrum. Somebody talking there, I think. Okay, thank you. And how it works? I ablate this target in vacuum chamber, and then laser radiation propagates through this plasma, as I told, and then analyze it in XUV spectrometer by standard methods. This plasma can be analyzed by different driving radiation. It can be either fixed laser, titanium sapphire laser, or from other lasers like OPA and so on. What in that case we can gain? We can create different sources of harmonics, which are not just simply harmonics, but some harmonics, different orders harmonic, and so on. So this broad and rich spectrum can be used for analysis of the features, spectroscopic features, and overall atomic features of the targets. This method also allowing to analyzing the variation of harmonic spectra in the case of the extended plasma and multi-jet plasma. You can see very big difference. It means that we can move most of energy and significantly amend and enhance harmonics in the short wavelength range. Probably you know that there are no coherent sources in XUV range, apart from a few X-ray lasers, but this method allows tunable creation of tunable sources of harmonics in this spectral range. Another method is the use of two-color pump of plasma. What means two-color? Commonly, people use single-color plasma. It is a single-color pump of plasma. When titanium sapphire laser uses for excitation of plasma. And in that case, for example, in case of silver plasma, we can see by red color, I show you only a few harmonics. But once we put, instead of single color pump, in that case was 1310 nanometer radiation, we use this radiation plus its harmonic, it significantly broadened the spectrum, extended spectrum, and created a range of harmonics up to the 20 nanometers. The same can be demonstrated in case of gold plasma. You can compare red and blue colors in case of single and two color pump, and in zinc plasma, the same here. Another interesting feature, nonlinear optical feature, is the single harmonic enhancement. As you can see in all the spectra, all of them represent some featureless spectra. Meanwhile, in case of indium plasma, it was observed that one of harmonics significantly, a couple of orders, can be larger than other harmonics. It's some sort of the source of single harmonic in case of indium plasma. And this method, which I further elaborate in the next pictures, is a very interesting approach to create some sources at the fixed wavelengths. Some other interesting features which observed at these conditions are studies of fullerens. Fullerens just demonstrated, and further I will show, that they have very interesting features from the point of view of analysis of their surface plasmon resonances. And these features will be shown a bit later. Third interesting feature, which distinguishes high-order harmonic generation in plasma from the high-order harmonic generation in gases, is the application of nanoparticles. Here I just show SEM images of nanoparticles of indium oxide and chromium oxide, which were ablated and two below SEMs are just the debris of those particles. And the same can be done with the carbon-containing nanostructures, like carbon nanofiber, carbon nanotubes, diamond nanoparticles, graphene and fullerenes, I told. Each of them demonstrates the same features like graphite when they disintegrate apart from themselves as neutrals. They have some ions in the range of C5 up to C30. And as a result, they have significantly stronger harmonic yield compared to the harmonic yield from silver plasma, which previously was demonstrated as the strongest metallic plasma, material for plasma formation and high order harmonic generation. Another interesting feature, how those single harmonic enhancement properties change from atomic medium to molecular medium. Here I just shown the spectrum of indium harmonics from indium plasma. Again, 13th harmonic is significantly stronger than all other harmonics appearing in this spectrum. However, once it becoming indium oxide, all of them becoming approximately the same without disappearance of effect of resonance enhancement. This resonance enhancement was demonstrated in manganese, chromium, and maybe in few other samples it could be demonstrated, and only in those cases we can create strong single harmonic enhancement experiments. Another interesting feature is the surface harmonics. When strong femtosecond beam interacts at, say, some angle around 45 degrees, from the surface, at the specular direction, goes high order harmonics, both odd and even harmonics. My analysis of those harmonics, I just shown here between 10s to 18s, from fullerenes, from indium and aluminum plasma, allowed me demonstrating the features of those materials in different spectral range. And by analysis of them, we can make judgment about the atomic structure, about the optical properties like oscillator strength, and so on. For example, like there, nearby to this spectrum of manganese, there exists some line with very strong oscillator strength. And from this spectra, we can analyze this line. It's such sort of first attempts to demonstrate laser-induced high-order harmonic ablation, high-order harmonic generation spectroscopy. It's some sort of the high-order nonlinear spectroscopy. Other interesting features, again, returning back to the low-order nonlinear optical properties, are application of quantum dots. Quantum dots are very small particles in the range of between 2 to 4 nanometers, where quantum confinement and local field enhancement are very strong and can create very interesting and demonstrate very interesting features, like enhancement of many nonlinear optical properties. Here I demonstrate enhancement of such a property like optical limiting. So with increase of energy of input pulse, propagation becoming remaining the same, however, then it stabilizes, and this quantum dot can be used for the optical limiting about which I told earlier. We use different quantum dots based on metal sulfides, and such as cadmium sulfide, zinc sulfide, and alloyed sulfides. As well, as we analyzed the low-order nonlinear optical properties like nonlinear refraction. It shows positive nonlinear refraction and two-photon absorption in different wavelengths. Returning back to high-order harmonic generation, I would like to say a few words about the properties of those harmonics. Important property of harmonic is their coherency. The analysis using the double slit Young interferometer just demonstrated that both resonance harmonic and non-resonance harmonic show very strong, large visibility, demonstrating good coherence properties of this material. Another feature is a demonstration of stronger conversion efficiency of high-order harmonics in the case of plasma compared with gases. Here I show the low-order harmonics generating in carbon plasma and in argon gas. You can see that even at these conditions, conversion efficiency for low-order harmonic generation becoming stronger. This method also allows analysis of complex molecules. Here I just show two images of the DNA components like uracil and thiamine. In case of uracil, I was able demonstrating strong high-order harmonic generation, while in case of thiamine, no any harmonics were observed due to addition to the methylene part to this molecule, which fully suppresses this effect. Another interesting feature is application of different pulses for high-order harmonic generation. In case of relatively long laser pulses, here I show a case of high-order harmonic generation spectra from the manganese plasma when they used relatively long pulses, 30 femtosecond pulses. You can see here very strong 31st harmonic, which is the beginning of the second plateau, which spreading up to the harmonic hub above the 100 orders. However, once I used the 4 femtosecond pulses, those are a few cycle pulses, only single harmonics can be clearly seen in that case, and it is a way to create single harmonic in the range of 50 eV, which has not been demonstrated by other teams, and analysis of this material now carrying out in different laboratories around the globe. Next feature is the application of higher pulse repetition rates. In case of high pulse repetition rates, you can destroy the target, create craters, and change the properties of plasma. However, if you put your target on the rotating translating stage, and if this target rotates, then ablation by pulses do not destroy target, and you create source of high-order harmonic generation even without any change of position of targets up and down, and create stable harmonic generation. How it can be demonstrated? In case of rotation of target, more or less stable harmonics going, and once it's stopped, motor stopped, it drastically drops up to low level. These methods allowed us to show that in case of nanoparticle plasma, we have significantly stronger conversion efficiency compared to the ablation of bulk material with the same elemental state. Here are spectra from aluminum, ablated bulk aluminum target, and here from ablated aluminum nanoparticles. You can see that at least 10 time amplification of conversion efficiency. Next interesting feature is interference of the long and short trajectories, so-called when apart from the on-axis harmonics, you can see interference of short and long trajectories with long trajectories of electrons and can analyze those materials through the analysis of those rings. During those experiments in different places, I was able analyzing depending on a dependence of high order and in that case low order harmonics on the delay between heating pulse and driving pulse. It has been shown that there is some maximum, and it is obvious. We have to find conditions when the largest amount of particles comes to the optical axis of propagation of femtosecond pulses. In that case, we can very strong nonlinear optical effects without any appearance of any plasma lines. In that case, also, we can demonstrate very good optical limiting effect, especially for some specific wavelengths and specific pulse durations. Another interesting feature is application of the nanoparticles and complex materials. Currently in China, a few groups actively working with the perovskite as the materials, future materials for solar cells, and analyze their luminescence, spectroscopy, and nonlinear optical properties are of the utmost importance for demonstration of the efficiency of this material for the creation of the next generation of solar cells. Attempts to use this material of as a medium for high order harmonic generation, as well as for some other features like analysis of nanostructures of those materials, also allowed through the third harmonic generation, like shown here in case of silver plasma, analyze those materials and demonstrate the advanced properties like those demonstrated advanced properties as the good luminescent materials. Next feature is the creation of non-spherical nanoparticles. Everybody can chemically create spherical nanoparticles. However, many previous studies have shown that if we have non-spherical nanoparticles on the edges of those non-spherical nanoparticles like cuboids or square-like particles, very strong local fields significantly increase nonlinear optical effects. I was able, with my team, creating those features in the case of indium plasma. Those are cuboids and square-like. Those rod-likes in case of zinc oxide nanoparticles. In case of copper, we have some urchin-like and ellipsoid-like. And in case of aluminum, we have some triangles and bow ties. So those features were analyzed, nonlinear optical features were analyzed here, and just here I just show them some of those properties when, apart from saturable absorption, we were able to register reverse saturable absorption in these materials. And from these properties, we can analyze the lifetimes of those transitions and make some judgment and conclusion about the application or in different laser equipment of such systems of non-spherical nanoparticles, particularly in case.
Sorry, Rashid, your no voice. Rashid, now your voice is on mute.
We don't hear you.
Do you hear me?
Yes, now we hear.
But now your presentation.
Okay, okay, one moment. Let me. Do you see presentation? Do you see presentation?
Yeah, we see presentation.
Okay, thank you. So another feature is the variation by nonlinear optical methods of the features of targets. Particularly, we were able changing of color of metals. Here I just show some images by creation of nanostructures in different materials. It allowed us smoothly change the properties of surfaces of materials. Alongside with this, we analyzed the nonlinear optical properties and created some protocol when high order nonlinear optical properties can be changed to the simple excitation of incoherent emission in different materials. Due to shortage of time, I see only 8 minutes. I just skip many things and just show that in some cases we again created single harmonic generation, analyzed it in case of two-color pump, and demonstrated the possibility of efficient harmonic generation with the decrease of the efficiency of single harmonic generation. Some other features were also observed in case of third and fifth harmonic generation in plasma, as well as analysis of such materials like candles or some flames, and analysis of theoretical properties, theoretical analysis of properties of ablated materials and dynamics of creation of nanoparticles. Finally, I would like to show you periodic table where previously only gases were used for high order harmonic generation. During my activity, I analyzed almost all periodic table solid state materials, which are not non-radiative solid state materials, and some of them demonstrated very efficient high order harmonic generation. I demonstrated stronger harmonic generation in metal plasma containing with argon plasma. In some cases, it was possible to demonstrate much more stronger harmonic generation in case of rotating target compared to the fixed targets, and very strong single harmonic generation. It is logarithmic scale, which shows that it is around 10 times stronger in some plasmas like tin plasma and so on. And again, returning back to quantum dots, we demonstrated that those quantum dots can also be used for the quasi-phase matching, and we demonstrated strong variation of the groups of harmonics in different spectral range ones using different configurations of multi-jet plasmas. Finally, I would like to say that we also analyzed so-called nonlinear scattering during that scans and demonstrated some features both in case of some dyes and in case of some structures when nonlinear refraction shows nonlinear scattering significantly change the behavior of those materials. Some properties of carbon particles compared with strongest indium plasma demonstrate that they are comparable, but at the same time they are the same as strongest high order harmonic generation in that case. And finally, I would like to say that those methods allow demonstrate so-called 3D picture. Once depending on the number of shots, you can analyze the and create the conditions for analysis of high order harmonics in different plasma materials. And finally, one spectrum which shows the just simple spectrum in case of common method of high order harmonic generation, and once you create filaments and then send beam through this propagation, you propagate through the plasma, you create much more stronger and extended and broadened spectrum of harmonics. I made such lectures in many countries. Briefly, I just shown here them, and interest to this field of nonlinear optics is very strong, and I think that it could be actively elaborated in Latvia, and this is one of main tasks for which I was invited in Latvia. Here our main goals are nonlinear optics, quantum optics, and photonics. And photonics, as you know, it is everything about photon. What we want to do. Our main fields are nonlinear optics, quantum optics, laser-induced breakdown spectroscopy, nanostructuring, nanomaterials, and applications. Some bureaucratic things are presented here. We would like to make some structural changes in the studies of photonics in Latvian University, applied with projects, collaborate with many groups, create laboratory of nonlinear optics, make some joint visits and publications. First steps of these collaborations were demonstrated recently with analysis of the meteorites from the Museum of the University of Latvia, where we analyzed metallic, so-called iron meteorites, and oldest meteorite from found in Latvia. It is so-called Baldonas meteorite in 1891. And recently some people approached to us to analyze another meteorite, which it is the first meteorite found during last 130 years on the territory of Latvia. And we have demonstrated that this meteorite, it is a optical spectra obtained using the laser-induced breakdown spectroscopy, similar to the to other meteorites of similar structure. So it is some sort of first step of confirmation. Now we are doing the SEM and EDS measurements and confirmation of this process. Another features which we are doing with the Institute of Solid State Physics are analysis of the properties of some molecular liquids, particularly carbon disulfide. For example, yesterday, Optical Materials published our first paper on this on that matter. It is joint paper with Institute of Solid State Physics. With them, we also analyzing some the mercury telluride quantum dot films, their properties with using the tunable sources of radiation. And beyond nonlinear optics, we would like to analyze nanoparticles formation, meteorites, laser-induced breakdown spectroscopy of geological species, nanostructures, art restoration, quantum dot application, wettability, and coloring of metal surfaces. A few projects have been submitted to LZP and Horizon Europe. Here is a list of our collaborators at that time. However, I have good ties with many countries around the globe. And finally, I just wondering, maybe we can make some collaboration with Institute of Atomic Physics and Spectroscopy. So we are open for these various joint projects. Summarizing, I would like to say that I established my methods to perform high-order harmonic generation in laser ablation plasma from various solid targets. So this method allowed to develop this field significantly, and some practical other applications are development of laser system for measuring the distances for satellites, laser welding of dental prosthesis, therapy, laser hardening of materials, increase of water repellency, laser marking, and nanostructuring. Many scientific aspects were analyzed in my 8 monographs. I published more than 400 papers, and my Hirsch index is 48. Thank you very much for your attention.